试都教你了，考试时候不教的。对。其实作者不会告诉你，就是他会总结说这种题用哪种方法，这种方法，看你这个有体现这种方法。然后他作者觉得这是这样的。我怎么看着我一看他那个内容啊，有意的。
All right. So why don't we take these first few minutes here? We've got a sample problem on the slide. It involves locals. See if you can trace the steps through this lovely function here. All right. So you've had a couple minutes to think about this little stepping problem. And I know that you probably don't remember much about local because, you know, you learned about it last Thursday and you had a weekend in there. And all right. Well, let's do it anyways. So let's turn the lights on. If I can find the switch. There we go. So we've got magic 2, 4. And since the arguments are values, we can just substitute them directly into the body of the function. However, it's not that simple, because we actually had to modify the function substitution rule at the very end of last class because since we can now have renamed things defined inside the body of the function, we have to be careful about the substitution. So since x is defined, again, inside the body of magic, we can substitute the y in, but we can't substitute the x in because there's going to be a different meaning for x. So this should give you, then, I think I got an extra bracket there. There we go. So that should be your first substitution step. Notice that we haven't replaced x. And again, that's because this x is this x, not the argument x. All right. Now, in our next step, we've got to deal with this local. A bunch of things are going to happen here, and it's all going to happen in one step. So the first thing that happens is that we're going to rename x and we're going to rename z to something unique. I'm going to use a frame number format, so you can use whatever way you want. And as I rename each of these values, I'm going to lift them out of the local and into the global scope. Now, I'm going to remove the local syntax itself and actually replace it with the body expression of the local. And as I do this, I'm also going to be substituting x for the new name and z for the new name. So you end up with this. And that all happened in one step. Now, if we look at the arguments to plus, they are not all values, and so we're going to have to do some more substitution steps. So first we're going to look at x001, and we'll replace that with 10. And then lastly with z001, and we'll replace that with 5. Negative 19. Any questions about this? Yeah.
Why don't you add the 10 plus 4 before doing that? Is it because it's a function?
Yeah, so the add operator and the multiply operator in Racket will only actually apply the add when all of the arguments are values. That is very different from how and or operate. So the way you're thinking about it is how do and or operate. And or, they operate differently for a very good reason. The reason why and or would operate by evaluate each argument separately is because in and, it only takes one false argument for the whole thing to evaluate to false. And so if I were to evaluate each of the arguments before looking at whether they were false or true, I would end up doing more work than was necessary. So and or have shortcuts. Things like add and multiply don't. Add and multiply, you have to evaluate the arguments completely before you can apply the operator. All right. Any other questions? I know it's probably hard to have questions about this because you haven't actually used it in anything, except maybe your dreams. I don't know. Maybe you dream in Racket. I hope you don't dream in Racket. That's kind of weird. But on assignment 8, which should be coming out this Friday, you will be required to use local. So you're going to get lots of experience with local very, very soon. And I know you're probably sitting there terrified of it, but there's nothing to be afraid of. Yeah?
The keyword's going to be required. Why is it required?
Because I said so.
That's a good reason.
It's the best reason, isn't it? No, to be fair, the functions you're going to be asked to implement on assignment 8 require a lot of helper functions. But the helper functions don't really make sense at a top level scope. So we are going to force you to encapsulate them in locals to give a nice package to your user instead of something full of messy things you don't want them using. It's more about let's make our code better. All right. So then, if you have a clicker, why don't you get it out? I'll give you 2 a minute, by the way. All right, so let's see where everyone's at. Most of you said B. B is correct. Arguments, function arguments, are only defined inside the body of the function. If I have magic and its arguments are X and Y, that X that is an argument only has that meaning inside the body of magic. That doesn't mean X doesn't have meaning outside the body of magic. It's just it can only have a different meaning outside the body of magic. All right. Now, since I gave the other class a freebie here, you've got 15 seconds to choose the right answer. Or be completely rebellious. All right, I'm stopping it, so. Everybody got it. All right, so just for the record, if you had selected the wrong answer for this one, for this freebie, everybody gets marks for the freebie, no matter what you pick. But y'all got the same marks. We don't have to worry about that. All right. Nobody wanted to brave being rebellious. All right, one more then. Another question about local. Again, you've got 1 minute to answer this one as well. All right, if you haven't pushed a button, I would push it now because I'm going to stop this. All right, so let's see what everyone said. Most of you said D. D is correct. indeed encapsulate data and functions inside of other things. And the reason why we would do this, amongst many reasons, is because often we don't want our user to see all of our messy helper functions, because they're really only meant for that function, not really meant to be called otherwise. Local is also letting you bind the same name to different values in different scopes. What that means is that, well, if you looked at that function magic, we had argument x, and we also had redefined x in a different scope to be something else. So you can do that. Now, that means that you can have the same name have different meanings at different scopes. And just because you can do that, for the record, doesn't mean you should. And in fact, if you, for assignment 8, submit to us code where everything in your local has the same name as stuff outside the local, that is, you didn't create new variable names, expect to lose style marks, because that is not readable. Just because you can do B doesn't mean you should. That's, sorry, a pet peeve, is you go into code and people have like a global definition for X, and then they have like a local definition for X. And so inside the function, you're sitting there, you're like, if you don't see that global definition, or you're just looking at the code really quickly, it can be really confusing what's actually going on. So to avoid confusion, just because you can do B doesn't mean you should. Now, we say local can only be used in the body of a function. That's not true. Allow me to demonstrate. So here we've got a lovely racket window. And I'm not going to put the local inside the body of anything. In fact, I'm just going to put it straight up right here. Like that. It's not in a function. It's not an argument to anything. No problem. Local does not have to be inside of a function. You can put it anywhere. And you can nest them inside each other, and you can put them in cons, and you can pass them as arguments. You can do whatever you want with them. All right. With that, those are all of the wonderful clicker questions we have for today. But before we go back to talking about local, there's one thing I would actually like to show you. So you've got your midterms back now, and if you haven't taken a look, please take a look at your midterm. You have an opportunity to submit a remark request up until, I believe, March 20th. Remark requests should be done through the online form. Don't send me an email. Don't try to get me to do it in person. Please don't hand me a sheet of paper. If you hand me paper, my daughter's going to take it and draw like dinosaurs on it or something. So, that being said, if you are on the fence about whether you should ask for a remark or not, and you have some resources at your disposal to help you make that decision. So I've been asked to point this out to you by our lovely ISAs. So if you go under assessment on the course website, there's actually the solutions to the midterm, or at least the ideal solutions, or the solutions that popped in my head when I was writing them solutions. They're actually here on the course website. And you have to log in, and it's gonna like spit your username as a watermark across it, but you can get a copy of the solutions, and you can use that to help you decide whether you should request a remark or not. And the other thing I want to point out, so you have the solutions, and that doesn't just include the midterm, that's actually for the assignments, and you can use that as a great study tool. The other thing I want to point out is below the solutions link, there's a post-mortem link. And I think this is something that's usually pretty much overlooked, but what this is we have all of our graders collect up the common mistakes that they found and assemble it into a file to share it with you. And this is so that you can see what were the common mistakes people made with each particular question. And this can actually be a good study tool for you, or if you haven't done so well on the assignment, this can actually be also a very useful resource for learning from your mistakes. And we also have a postmortem for the midterm up here as well, so that could be useful for you too. Now, on the topic of the lovely, lovely midterm that you guys had, I'm sure, you've been here, I don't know, maybe 4 months, or maybe you're a science student and you've been here a little longer, but there's this long-standing tradition that if you have a really high-scoring midterm, which, by the way, I got in trouble for, because it was apparently 8% higher than it's ever been, but I'm going to attribute that to the fact that you have more study materials than you've ever actually had access to before, so that's pretty cool. And I don't really care what the rules are either. But there is a tendency to believe that with a high midterm average, that you should anticipate the final exam is going to be absolutely brutal on purpose. I have 2 things to say about that. I don't play that game. Your final exam difficulty is going to be the same difficulty it was always going to be. I'm not going to adjust the difficulty due to the midterm average. I'm not going to do that. That might put you into a false sense of, this is going to be great. I got perfect on the midterm, and it's not going to be an on-purposely, overly brutal final, so I don't need to study. I want to warn you against that. Don't let your midterm score lull you into a false sense of security. The pre-midterm content is very easy. It's simple recursion, numbers, basic lists. There are no structures. The post-midterm content is significantly harder. You've got structures. You've got more cumulative recursion. You've got trees and traversal of those trees. You've got mutual recursion, which is a particularly nasty thing. You've got things like local, and you're going to have function abstraction, and you're going to have lambda, and you're going to have graphs. And as it turns out, all of the post-midterm topics are actually significantly more difficult. So I'm not going to make your final exam brutal on purpose, but I want you to be aware that the topics that are going to be more heavily weighted on the final exam are by nature harder. So don't use your midterm grade as a reason to not study, please. We will, of course, put out some more sample content to help you study. So some more tree problems, some graph problems, and things like that. So you won't be going into the final exam unprepared, but I just want to warn you of this. All right. So then, any questions about the final? Of course not. If you're wondering, yes, the school is considering preparations for the plague. Apparently U of T has already done so, but we're still on the fence. All right. So then, we ended last class, we were talking about some of the wonderful reasons why you would use local. And in particular, we had this list. We have clarity. That's for naming sub-expressions, and it's also for just producing a tidier piece of code. We also have efficiency. We can actually use local to avoid recomputation of values, which is pretty powerful. And then there were 2 that we actually didn't cover, which is encapsulation and scope. So just to go back to efficiency, we already looked at max, and our original implementation of max, if you may remember, had a runtime of 2 to the power of n, which is an exponential runtime, age of the universe, it's horrible. And we can fix this in 2 ways. One of the ways that we fixed it before was by creating a helper function and doing it that way. That took it down to linear time. But here's the problem. The helper function we would have created only has meaning to the max list function. So you created a top-level function that has no meaning to a user, and yet you've provided it to the user to use. So local, we could solve this problem in one of 2 ways. We could just internalize that helper function, i.e. Do what's known as behavioral encapsulation, or we can actually use the local to just take this implementation and not compute the same value 2 times. So all we had to do then was simply, inside of the else condition, in a single time, we will compute the maximum of the rest of the list. And then in the body of the local, we're going to say, is the first of the list bigger than the pre-computed max? This function mimics the previous one. There are no helper functions, and it also has a linear runtime. This is quite nice. So we were able to use local to improve our efficiency by preventing us from recomputing things more than once. And we can do the same thing with a binary search tree. Or not a binary search tree, but just a binary tree. So if we want to find a path to a node, then what we were doing before was we were going to check if the left subtree had a path to the node, and if it does, then we produce the path to the node. Otherwise, we look down the right. And the problem is, again, this is an exponential function because we end up computing the path to the node twice. We don't want to do that. So we can use a local to actually solve this problem. Now, we did solve it for the record before by using a helper. So we have this choose path u2. But again, what meaning does that function have to a user? Absolutely none. So why? Let's use the local. Let's get rid of the need for all of that. And this is what you're left with. So what we're going to do is, if the tree is empty, we produce false. If the key of the current item is the thing that we are searching for, then we produce an empty list, because remember, we're producing the path to the node. Otherwise, we are going to get the path to search for the item down the left subtree, stored in left. And then we're going to get the path to search for the item down the right subtree, stored in right. And then in the body of the local, we're simply going to check those pre-computed values and see which one is the right one to use. So we have no helper functions. We have a linear runtime again. This is actually really nice. All right. So that wasn't perfect, by the way. One of the problems with the previous solution was that if you find the item down the left subtree, there's no point in looking down the right subtree because you've already found it. And yet in this solution that we have here, if you find it down the left, we don't notice, and we still look down the right. So with nested locals, you can eliminate that. And that's what we would do here. We compute the path to the left subtree. If it exists, then we just produce the left subtree. Otherwise, then we search down the right subtree. This is more efficient, but that's really ugly. Be careful with local. Local is a powerful tool that you have at your disposal, but it's also the power to make your code really ugly and really unreadable. So be very cautious about how you use it. Yes, you can nest them into each other as many times as you want. That does not mean you should do it. All right. So the other idea that we have behind why should you use local is this encapsulation idea, which is really just the sense of I want to hide information from my user. Maybe I have a function. Let's write a function. Let's do this. Maybe I want to write a password checking function in order to let people proceed. But I don't want to expose what the correct password is, so instead of doing this, that's bad because a user can access that. What I could do instead, in my function to check password, I could just define the value I want hidden inside this other scope. And now that is not available to the user. So we can use local to encapsulate or hide information. Like constants, we can hide them inside the scope that they will be used so they're not actually available to the user to use elsewhere. Don't implement a password checking program like this, by the way. Bad idea. Pretty easy to break. All right. Another thing that we can do, and I've already mentioned this before, is we can actually hide all of our helper functions inside the function that they're used. And that's actually a really valuable thing, because if you remember all of the different helper functions that you've ever written in this course, would you agree that many of them were really only useful to the function they were helping? Think about a cumulative recursion. You've got a wrapper, which is the function you want the user to use. But the actual cumulative function was also at the top level. So technically speaking, the user could call it directly and do so incorrectly. We don't want them to be able to do that. Furthermore, that's making our top level scope really messy by having all these functions there that have a single purpose, only meaningful to the function they're helping. So we have behavioral encapsulation, which is letting us take all those helper functions, those single purpose helpers, shove them inside the function they're helping, and now you have a beautiful, clean top level scope that only presents functions to the user that they should actually use, and all of your little helpers are neatly hidden away from the user, and they can't use them, and they don't know that they're there. So, to show you what I mean by this is an cumulative recursive function to sum the numbers of a list. Now, traditionally, there would be a wrapper, and then a function that is the helper that does the actual cumulative recursion. And you need the wrapper because the cumulative recursive function needs to have that accumulator, and you don't want your user to actually have to figure out, what's the first value for my accumulator I should have? That's not on them, that's on you. So, we could have two top-level functions, or I could use local in the wrapper to shove the actual helper inside. So now I have one function. So here we have it, our sum list, and inside the local, I actually have the definition for the cumulative recursive function, which I then call internally. There's no external helpers. A user cannot accidentally call this with the wrong initial accumulator because it's not exposed anymore. We've encapsulated the actual behavior of this into ourself. It's nice and tidy little package. Now, here is another example of encapsulation that I don't agree with. This is insertion sort. Insertion sort required a helper. The helper was called insert. And what insert does is it takes a number and inserts it into an already sorted list. In this particular example, they have encapsulated it inside the isort function, and I disagree with this. And here is why I disagree with it. Suppose I have a list of students, and I've sorted you according to your last names. Suppose a new student joins the class, and I want to add them to my class list. I want to add an item to an already sorted list. Well, that's insert. That is a function that is very conceivably useful to our user. It is not specific just to the implementation of insertion sort. So in this particular case, the insert function actually does make sense to be at the top level because it's very likely something the user would find useful. Be careful, because it can be tricky to see which functions should be internalized and which ones shouldn't. That does come with time. For the record, on assignment 8, you're not allowed to have any helpers at the top level. It's all got to be inside. It's not as hard as it sounds. All right. So, unfortunately, we also have to talk about how do you deal with the design recipe for these encapsulated functions. You can't ignore it, but you don't have to do the whole thing. You are required to give a purpose and the contract and any requirements for an encapsulated function. But you do not have to give examples or tests for the encapsulated function. Now, does that mean you don't have to test your function? No. You should test every piece of code that you write. How else could you possibly know that it works if you don't test it? My recommendation is actually the following. Write the code as you normally would without local, where your helper functions are at the top level. Thoroughly test your helpers at the top level. Once you are completely convinced that that works, then figure out how to encapsulate them in the local, and then do that, and then test your whole function again. But it's really, really tricky to otherwise just barf out a local helper that works. By the way, that is actually the strategy I'd use. So anytime I want to internalize a rather complicated helper function, I actually test the helper completely outside the local. Once I'm convinced it works, then I actually embed it where it needs to go and do any touch-ups I need to do. So it's sometimes easier to do it that way. Now, there's some other advantages that local can give us, and one of those is getting rid of the extra arguments that go along for the ride with simple recursion. So you might remember we wrote a function that we wanted to count up from 0 to n, which we generalized to a function that counts from some base m to some number n. And then counting up from 0 to n is simply calling count up to from and passing n, the stopping condition, and 0 as the start place. Now, the thing that's going on here is that if you look at this function here, our base case, our value for n, is along for the ride. It's totally unnecessary. You're passing extra arguments into a recursive call that are not needed, and it's potentially using extra memory. You know what? We can get rid of n as a tag along with a local. So we can actually create this lovely function. So if I want to count up from 0 to n, this is the function that I have. So I take that count up to from and I encapsulate it, but you'll notice that its encapsulated version has a single argument instead of two. Here's the thing. We are counting up from m to n. N is the argument for count up to. N is an argument to this function, which means the scope of n is the entire body of n, which means n is not only defined in the function, it's actually available for use inside the local as well. So we don't need to turn it into an argument because it's already there. It already exists. It's already bound to the correct value. So we can take that for granted, eliminate it as an argument from the encapsulated function, and just pass in m, the value that's actually going to change. So that's kind of neat. Kind of cool. Another place that shows you an example of where we can get rid of extra parameters due to scope is looking at our multiplication table. So you might remember we made a multiplication table where we specified the number of rows and the number of columns. And so in this case, we have 3 rows. Starting, we've got row 0, row 1, row 2, and 4 columns. So column 1, column 2, column 0, 1, 2, 3. Remember in CS, we always count from 0. Now, if you look at our original implementation, this is what we had. This is not a nice implementation. Now, it's not a lot of lines of code, but the problem I have is that all of these functions are at the top level. They don't need to be. Because things like rows 2 and calls 2, so this is making each individual row, and this one is creating the rows as a whole and appending them together, and then we've got the wrapper up there. So we've got these 2 functions here which don't really have meaning outside the multiplication table function. And then on top of that, if you actually look at these recursive functions, they've got these values that are going along for the ride. We can actually simplify this quite a bit with a local. So here it is. So we're going to take rows 2 and calls 2, we're going to shove them inside a local. And then you'll notice that we actually get rid of the argument nc and nr. Because in the body of this function, they don't change. Ever. In the recursion, they go along for the ride. Their value's not changing. So we don't need to pass them into here, the local's body expression, because they exist in a scope that is higher than us, therefore we have access to it. So we get rid of nr and nc as arguments, and now we have a nice, simple, and encapsulated piece of code. It's kind of neat, right? And by the way, getting rid of those arguments that go along for the ride, that's part of after you've tested your helper function and you shove it into the local later, you have to check for things like that. Are there things that I could pre-compute? Are there arguments I could get rid of because they're already defined? So those are the tweaks you do once you put it inside. Any questions about this particular example? All right. Some terminology then. So, a binding occurrence. Anytime that you define a name to be a thing, you are binding a name to that thing. You are assigning a name to that thing. That is a binding occurrence. Another kind of binding occurrence is function arguments. So if I have a function magic that has named parameters x and y, when I call magic with values 2 and 4, I am binding within the scope of the function x to 2 and y to 4. So there are two different kinds of binding occurrences. And then we say a bound occurrence is the use of that name for that particular binding. And then a lexical scope is within some scope, what are all of the what is the meaning of a particular bound occurrence? So in a lexical scope, what is the meaning of x going to be? Under which of its binding occurrences would you be using in that particular lexical scope? The other thing is global scope. Global scope is anything that exists at the top level. Now, are there more scopes than that? Yes. There's file scope, there's program scope, there's all different kinds of scopes. We're not going to deal with those so much, but if you move on to CS136, and I do hope that you do, you'll learn all about all kinds of fun scopes. All right. Any questions about this? Right. Well then, I would like to move on to the beginning of probably my most favorite thing in this language. But before I do, one last thing that I want to say. And that is, just by show of hands, how many of you in this room are C, C++, Java, C#, regular language programmers or have some experience with it? Okay, good number of you. You've just seen us define a function inside of another function. You cannot do that in C. You cannot do that in C++. That is something many languages do not support. So yes, in C and C++ you can define constants at different scopes, but in those languages you can't define functions inside of other functions. That is pretty much unique to our functional worlds. So if you're going home tonight being like, yeah, I'm going to define all my helper functions in my C program inside my C function, it's not going to work because it's not supported by the language. And if you don't like that, then you can join the C programming language committee and change it. But I would warn you that that committee takes like 20 years to decide anything. All right. So, my favorite thing, finally. So this is module 13, by the way. And this is lots and lots and lots of fun what we are about to do. So, we have this thing called first class value. And a first class value is something that can be consumed by a function, produced by a function, bound to a name, and so on and so forth. Functions are first class values. So you know that numbers are first class values because you can pass them in as arguments. You can shove them in a list. You can produce a number as a result. You can assign a number to a name. Functions are also first class values, just like numbers. I can pass a function as an argument. I can produce a function as a result. I can bind a function to a new name, and I can store functions in a list. Not evaluated functions, but just the actual function themselves. And this may seem very weird, like why would you do this? But hopefully by the end of today, you will see why this is both super powerful, but also super awesome. So, first off, again, for those of you who have experience in programming in other languages, what you are about to see may not be supported by your language of choice, or may not be supported well. So certainly in languages like C and C++, we can pass functions as arguments, sort of. It's ugly, it's nasty, but you can do it. What you're about to see, to pass a function as an argument or store it in something, in Racket, I've never seen it done more simply. You don't treat the function as anything more different than a number. Treat it just like any number or a character or a string. It's not that easy to do this in other languages. So this is actually a real big power for a language like Racket. So just a quick example of doing this. So first off, you're going to need to change your language level to intermediate student. Mine is set to intermediate student with lambda because I like using lambda. We'll get to lambda, don't worry. And if you're curious, what is this lambda thing she keeps mentioning? That's a function that has no name. Because you might need a function that has no name. We'll do it later. But for now, change your language level to intermediate students, and then you can write this magical function foo here. And foo is really, really cool, and they don't have enough examples here in the notes. So what I'm going to do is I'm going to implement foo over here in Racket, and I'm going to show you just how cool this is. So I'm going to define foo, and it takes 3 arguments. And the first argument is going to be my function, which I'm going to turn around and apply that function f that I passed in to arguments x and y. This could be a one-line function. Okay, we're going to run it, and now the fun starts. So what can we do with this thing? Well, I can use foo to add 2 numbers together. There we go. I pass the add operator as an argument in the exact same way that I pass the numbers, because a function is a value. And then inside the body of foo, I apply my function I passed in as an argument to the other 2 arguments. So my function foo is capable of adding 2 numbers together, or I could use foo to multiply 2 numbers. And you might be sitting there thinking, okay, I see that this function foo works for binary operators. It works for more than binary operators. We can do more than math with this little sucker here. We could, for example, compare 2 numbers. I could check if 4 is equal to 6. Yep. What if I pass in 3 numbers? So that would violate the contract for this particular function. So we haven't given a contract here for a reason, but the contract for this would be very specific, such that we are stating that the first argument has to be a function that accepts 2 arguments. If we were to pass in 3 numbers here, it would give us an error. Yep. What is the data type for a function? It's contract. Yep. No, the type of a function is that function's contract. Let me draw it for you. We will cover this not today, but on Thursday. But since you've asked the question, I will give you the If this was just for working on numbers, then we would do something like foo. Yeah. If we wanted to do this for anything, then what we would do, and I'll explain this on Thursday's class. We might do something like that. The contract's going to get very complicated. But the type of a function is its contract. All right, I'm going to erase that. Now this is boring. All I've done is math with this. And I said I could do more. So we did some equality comparisons. Nah, I want to do something more fun. I can use foo to cons an item onto a list. I can use foo to append two lists together. It's pretty neat, isn't it? This one function that could technically be one line of code, I can use it to do pretty much anything that takes two arguments. What I have just created here is an abstract function. I have abstracted the idea of functions that operate on two arguments into a single one-line function that I can apply to all of those possible cases. Now that may not make sense to you, so we have a longer example here in the notes that I think is actually pretty valuable. So we're going to deal with lists of things. So first we have a list of symbols. And I want to remove all occurrences of the symbol apple from my list. So I write a function called eatApples. eatApples is going to remove all occurrences of the symbol apple. If you actually look at this implementation, it follows the simple recursion template for a list of symbols quite closely. If the list is empty, we produce empty because we are producing a new list here. If the current item is not an apple, that is, if this first item of the list is the thing I want to keep, then I cons the first of the list onto the result of removing apples from the remainder of the list. Otherwise, I need to remove this item, and so I produce the result of removing apples from the rest. Yeah. So we are checking if the we could rewrite this. You could. Yeah. But you would have had to change the two recursive cases spots. So I would have had to put eat apples with that and then flip it back. I didn't write it, so. All right. This function removes apples. And you write this function. And the next day your boss comes to you and says, I know you wrote a function yesterday to remove apples from your list, but I don't like bananas, because I actually really don't like bananas. I think they're nasty. So I want you to write a function now to remove all occurrences of bananas from the list. So you go and you write another function called throw away bananas that takes a list of symbols and removes the banana symbol from the list. And then I come back to you the next day and say, you know what? Pineapples don't make me feel so good. Can you write a function to remove pineapples from the list? And so you go out and you write another function, except this one's going to remove pineapples. And then I come back a day later and say, yeah, you know that fruit rambutan that's the little balls with all the wiry hairs on them? That fruit will kill me. So can you write me a function to actually remove those from the list? Which, by the way, that fruit will actually kill me. So what's the problem that we just have now? Every time I want you to remove something from the list, I ask you to write a brand new function. And if we were to actually write them here, they all look almost identical. The only difference between each of those functions I just asked you to write was the fact that, well, one we're comparing it to apple, another we're comparing it to banana, a third one we're comparing it to rambutan, another one we're comparing it to pineapple. Now you might be thinking the obvious solution here is to parameterize the thing you want to remove. Okay, that's actually fair. But we can go a step further. So here's another function. It's not dealing with a list of symbols. It's dealing with a list of numbers. Suppose I want to write a function that removes all of the even numbers from a list. So if the list is empty, I produce empty. If the item is odd, I keep it, and I cons the first item onto the result of removing all of the evens from the rest of the list. Otherwise, I just remove the evens from the rest of the list because the current item is even and I don't want it. By a show of hands, how many of you would say this function is essentially identical to the one we just had up? Because it is. It's absolutely the same damn function. Yes, it operates on a different type. Yes, the thing we were trying to remove is different. But the actual base algorithm, the template, is the same. And maybe your boss asks you to write this, and then they come back the next day and they say, hey, can you write me a function to remove all the multiples of 3? What's going to happen is you could write individual functions for the eat apples and the throwaway bananas and the keep odds and the throwaway multiples of 3. You could write functions for each of those. But you're going to end up with a program file that's tens of thousands of lines of code that is essentially copy and paste of the same damn thing, just a teeny tiny change to what is the thing you are keeping. The body of these functions, the algorithm we are using here is the same. And we can actually not just abstract this for symbols and abstract it for numbers, we can extract it for any type. We can create one function that can implement both keep apples, or eat apples, and keep odds. And any of them that we wanted to do. And the function is going to follow that same kind of template that our keep odds and our eat apples has, but there's one change. Instead of having a specific predicate to check, is this the thing we want, we're going to parameterize not the thing we want, but the predicate to check if it's the thing we want. So now we're going to call this function myFilter, because that's what these functions are all doing. They are producing a filtered list. You give me a list, I filter out some things, and I give you a new list. So we're going to call this abstracted function myFilter. It consumes a predicate. The predicate is to check, is this something I want in my list? And it consumes a list. And then if you look at the body of this, it mostly looks the same. It's a teeny exception. Indicate we're going to, empty is the same, but then we're going to use our parameterized predicate function to check if the first of the list is the thing we want. Otherwise, or in the case where we need to remove the thing from the rest of the list, we keep just passing that predicate along. Exact same template here. But now we've abstracted it, so not only does it work for numbers, but it also works for symbols, it works for structures, it works for whatever the heck you want it to work for. It's kind of cool, right? I think it's kind of cool. So here's an example of tracing through it. We'll go through this actually quite quickly here. So you've got myFilter, and I want to this time keep the even numbers. So the predicate I pass in is even. So we are filtering. We are passing a predicate that answers true to the things I want to keep. And then I pass in my list. So 0 is even, so I keep it. 1 is odd, so I throw it away. In the next line, I get 2 is even, so I keep it. 1 after that. 3 is odd, so I throw it away. And then I keep 4, and then I'm in my base case, and I have empty. Pretty cool, right? Now, this kind of function here actually has a very specific name. This isn't just an abstract function. This is an abstract list function because it's a function that is abstract. That is, we have abstracted the specific use away into a generic function, and it works on a list. And abstract list functions are totally awesome, and there's a lot more of them, and we'll see more. So we can then use my filter, and maybe you did want a specific function called eApples. Okay, you can do that. What you can simply do is create eApples and have eApples call my filter. And now all of those filter functions that were specific, you can still have specifically named ones, they will simply call the abstract list function my filter and pass an appropriate predicate along. And you're done. You went from possibly tens of thousands of lines of code to just a teeny little tiny bit of code. Now, you might be thinking to yourself, all right, so I actually have to write this my filter function anytime I want to filter a list. Nope, you don't. It exists already. It's just plain old filter. So if you turn on intermediate student, you will automatically get the wonderful filter function. And it really does work with anything. So I'd like to demonstrate some other things that you might do with filter. So let's go over here to Lovely Racket again. And something you might want to do is maybe you want to write a, maybe you need to filter students according to who is going to pass CS135 and move on to CS136. So I'm going to first create my students. They have a name and they have a program average. And then I'm going to make a list of students. And I'm going to choose names for students based on the worst baby names ever list. So if you're wondering, these are all names that people have actually named their kids. Or tried to. And if you don't believe me, look it up. This one's from New Zealand and they actually got blocked. Cheese is great, so cheese gets a high score, right? Pardon?
The last one in next student.
Oh, thank you. Spelling's not my strong point. There we go. Yes, somebody named their kid that. I believe it was in the United States. And I believe it was more than one person, too. All right. So we have a list of student structures. And I want to filter this list according to who is going to be able to move on to CS136. So let's assume you needed to achieve a 65 in this course in order to go into 136. I don't actually know what the value is because they keep changing it. All right. Now, I need a predicate function, and since I don't have lambda, I'm actually going to have to write a proper predicate here. Sort of. So let's do that. So we'll define our predicate. It's a really bad name, but let's do it anyways. 136 question mark. And it's going to take a student, and it's just going to produce true if the student's grade is higher, greater than or equal to the cutoff. Okay, there's our predicate. Now let's run this. There we go. All right. Now let's filter our list of students and see who gets to go on to CS136. So, built-in list function, you don't have to implement it unless we ask you to, like on an exam or something. So, filter, and then I pass my predicate, which is 136, and then I pass students. And there we go. We have number 19 bus stop, cheese, and chlamydia all get to go on to CS136. What I'd like to point out here is look how little code I wrote. I have a predicate, it's like one line, and then I call filter. This is why Racket is actually a fun language. Because if I tried to write this in C, I'd have to write the filter function, which would be a pain in the butt, and then it's not this flexible. I can do it in C, but the number of lines of code in C is going to be like this, and in Racket, it's like 2 lines. That's really awesome, actually. Then I know all the code that you've written in Racket right up till now has been like lots of lines of code, and on assignment 8, you're gonna have lots of lines of code even still. But on assignment 9, which is your last assignment, you're gonna get to use these. And your code's gonna go from this to this. These abstract list functions are really, really awesome. All right. So, what are the advantages of this functional abstraction stuff? Lots of advantages. One of them is you can take a block of code that is possibly tens of thousands of lines and turn it into maybe 2. You're going to significantly reduce how much code you have. And the reason you're able to do that is because you don't have to cut and paste the body of a bunch of similar functions. So you've got some template, and you've got a bunch of functions that all use the same template. Well, instead of copying and pasting it everywhere, you just use an abstract list function, or create your own abstract list function, and then just use that. The advantage, of course, of not having cut and paste code, or a bunch of functions that are all essentially repetitions of each other, is if you made a mistake in the first one, it won't propagate to all the others. It's easier to fix because all you have to do is fix the abstract list function and not each individual function. So this is going to give you a beautiful, super useful abstract function that can not only be used for the things that you intend to use it for, but for many different things. Things you can't even imagine it being used for. You can also use these abstract list functions to reduce your code, to make it more readable, to make it more maintainable. They're really, really great. Really great. And there's obviously more than just filter. So there's map, there's fold L, there's fold R, there's build list. There's all different kinds of them. We'll talk about them more later, but I would like to introduce you to one other one that's really fun, and that's called map. Map's one of my favorites. I see some people perk up to the concept of map, probably because you've heard of MapReduce before. And guess what? This is that map. So how many times have we asked you to apply a function to each element of the list? Like all the freaking time, right? And you had to write some recursive function to create a new list that applies that function to each thing. So you want to add 1 to every number in a list, you actually had to write a function to do that. Well, map, the abstract list function, is a one-liner that applies the provided function to each element of the list. So map, which we'll talk about another day, I want to add 1 to everything in my list. Ta-da! 1 line. Got rid of like 6 lines. It's awesome, right? I think it's awesome. One of the things, by the way, I really like about this language is the implementation. The actual execution of this code may not be the fastest it can be, but I've always found it like this little puzzle, this little challenge of how can I solve a problem in the fewest lines of Racket code possible? And functions like map and filter really help with that. All right. So we've just seen a whole ton of examples of actually passing functions in as arguments. That is not all you can do with them. We can also produce a function from a function. So they can also be returned. So this is a function called makeAdder. And it has an argument n. And inside it has a local that defines a function f with argument m to be n plus m. And the body expression of the local doesn't actually apply function f, it produces f as a value, which means makeAdder produces a function. And if I pass makeAdder the number 3, you can see what's actually going to happen. So I call makeAdder 3, and then we're going to replace all occurrences of n with 3. So here's my local now. And then I'm going to create a new definition for f with a unique name. And now I have defined f42 consuming a single argument to be 3 plus n. And I am then going to get rid of my local and I produce just the body expression, which is just the value that is the function. It's not evaluating the function, it's just passing the function as a value to you. Now you might be wondering, what the hell am I going to do with this? Well, it produces a function, which means I can put makeAdder 3 in the place where my function would be, and then I can pass an argument to it. And what you see here is that I now have f42, my function, and I'm passing to that function 4, which will substitute into adding 3 plus 4. makeAdder 3 produces a new function that adds 3 to whatever value you pass to it. It's kind of neat. You have essentially just made a little function factory. You wrote a function that produces functions for you. It's kind of fun. And maybe you know, here's the thing. Why would you make a little function factory like that? Well, maybe you want to create add 1, and maybe you want to create add 2, and add 3, and add 4, and add 5. Do you honestly want to do that for each and every one of them? Instead, or maybe it's something more complicated, because this is obviously a really easy one. But instead of actually doing this for each one, all I can do is I can say define add 3, makeAdder 3. Define add 2, makeAdder 2. makeAdder is a little function factory. It's an abstract function that makes functions. This is kind of a bad example, but it shows you that you can indeed have one function produce another function. It's kind of fun. All right. Now, there's a little trace through there. And this will help you kind of see how this is working. But one thing I also want to say, you might be thinking, well, I can only bind a function that I just created from like a local. Nope. You've seen 2 of the ways that we treat functions as first-class values. So we can produce, or we can consume a function as a value, we can produce a function as a value. We can also, with this example, you're seeing us assign or bind a name to a function. And it's not just the ability to bind a name to a function that some other function produces. We can do something else that you probably shouldn't do, but can technically do. I can do this. I can take built-in functions in Racket, any function, and I can bind it to a name. I can bind any function to a name. And now, I can do Let's act 2 and 3. Okay, so to be honest, this is not the intended use of this particular thing. So this is another one of those, yes, you can do it, no, you probably shouldn't. So it does make sense for our little function factory make adder. It does make sense to bind the function it produces to a meaningful name so that we can actually use it in a meaningful way. Redefining what the add operator is called? Don't do that. Yeah.
Are you able to change the definition of method? Like, can you make
I've never actually tried to do that. Do you want to try? Let's find out. I've honestly never tried to redefine numbers in this language. I don't think it'll work. Yeah, didn't work. That's no fun. So some context to this. I wanted to actually redefine the brackets in racket to be something else because I was trying to figure out what is the most obfuscated piece of racket code I could write. Yeah.
Would it not be possible to make that racket always expect some sort of function call after the bracket?
Yeah, so I mean, the way we treat racket is all these substitution steps, but unfortunately the substitution steps we actually use in the notes are different from racket's real ones. So I was curious to see if it had any kind of like pre-processor substitutions like C and C++ have, where I can redefine all that stuff. But unfortunately they didn't.
Why don't we follow this step?
Because racket is likely making a lot of optimizations to save a little time, and it can do that. We're following more closely, I want to say, like the calculus rules, like theoretical rules. We're very close. All right. Nope. Did you have a question? Okay. I'm going to leave that there for today. We will continue looking at functions as values and more abstractless functions on Thursday. Please don't bug your TAs and redefine what the add operator is.